Hey guys, welcome back. This is 6.5, measuring delta E for chemical reactions. Constant volume calorimetry. That's actually where is going to be our main focus of 6.5. If you recall, in 6.2, delta E, which is internal energy, was equal to Q plus W. That was a formula that we were given. We were also, or we've recently been witness to, Q equals MC delta T. That's our measure of heat. I'm not sure if we've spent any time talking about the work equation, but work is equal to negative P delta V. This is where we're going to skip just a little bit, and basically all our calculations that we do in chemistry or in AP chemistry are at constant volume, which means if our volume is 0, everything else up here becomes 0 as well, because 0 times whatever is going to be 0, and so work becomes 0. And if work is 0, we can say that delta E, or our internal energy, equals heat, and that makes the calculations that we do so much easier. And so that's a lot of what we do in AP chemistry as well as lower levels of chemistry as well. Calorimetry is the measure of thermal energy exchanged between reaction and surroundings via temperature change. So basically, this is the practice of what we did in 6.4, part 2, where we were taking energy of reactions is absorbed by the surroundings. We even have a specialized piece of equipment called a bomb calorimeter. A bomb calorimeter is a specialized piece of equipment that is sealed, so there's no volume change. And that gives us a formula, QCal equals Ccal times delta T. Ccal is the heat capacity of the calorimeter. And this will actually have to be given to you because it'll always say it was done in another reaction. Delta T, as you recall, is T final minus T initial. Since we know heat is released by the action has to be gained by the surroundings, negative Q of the reaction equals QV equals delta E. And delta E is what we're interested in right now. So most of the time, to find our answer, we're just going to go ahead and divide our moles that actually reacted by delta E. And so the key here is to remember that we're going to be dividing how many moles and find delta E. So we're going to divide by that. So the very first thing that I want to do here is read through this example problem. We've got when 1.01 grams of sucrose, which formula C11H22O11, undergoes combustion in a bomb calorimeter, the temperature rises from 24.92 to 28.33. We're supposed to find delta E for the combustion in kilojoules per mole, and our heat capacity of the bomb calorimeter is 4.90 kilojoules per mole. Degree C. So let's just start plugging our stuff in. Let's use our formula first. Q equals Ccal times our delta T. So our Ccal is 4.90. Our temperature change, if you recall, is final minus initial. So we're going to take 28.33 and subtract 24.92. This comes out to be 3.41. So now if we time these two together, this gives us Q of our reaction, which is 16.7. But if you recall, Q reaction equals negative QV, or this is actually QV. That's maybe the better way to think of it, is QV. And QV equals negative Q of reaction. So at this point, we change our sign to negative 16.7. And that is negative 16.7 kilojoules per mole. So what we've got to do at this point is we've got to convert our grams, 1.010 grams, and we're going to divide by the molar mass of sucrose, which is 342.3 grams. And that'll give us kilojoules per mole on the bottom. And so when we type this all out, the number that we get is negative 5,660 using sig figs, and that's kilojoules per mole. And there you have it. That's how to use a bomb calorimeter and do calculations with said bomb calorimeter. Thanks. See you next time.